This is the 6-1 to 6-3 review. Calculators still are not allowed. And in this problem 3, we are working with kind of a combination of 6-2, because we're dealing with volumes of revolution, and then we're also thinking about section 5-1, where instead of actually finding the true value, we're doing an approximation using slices with a width other than dx. We're going to actually have an actual width. It's not a differential. So this first one says a solid is formed by revolving the curve y equals the square root of x about the x-axis, and we want to estimate that volume using 5 subintervals of equal length, and we want to be perpendicular to the x-axis using, let's see, did we say, circumscribed. So that means we want to use values that are too large in each of our subintervals. So we're going to start first by drawing our curve, which is the square root of x, and we're going from 0 to 5. So if we label our intersections here, we've got a 0, 0, got a 0, 5, oops, excuse me, a 5, 0, and a 5 root 5. And this time, instead of drawing one representative slice, we want to cut this into 5 subintervals. So we've got a 1, 2, 3, 4, 5. And we want to construct circumscribed cylinders. So that would involve first doing the circumscribed rectangles. And then we're going to rotate each of these rectangles around the x-axis. So when we do that, we're going to get something that looks an awful lot like a wedding cake tipped on its side. Hopefully you can kind of see that. So our goal is to find the volume of that wedding cake now. So that means we've got to add up the 5 layers of that cake. So how do we get the volume of one of those? Well, the volume of one of those is going to be the pi times the radius squared. So we're going to be summing up pi times the radius squared times the height. And the height on each of these is our delta x. So let's remember that delta x was b minus a divided by the number of subintervals. So that's going to be 1. So we're going to have that for each of them. We'll have a pi times a radius squared times a 1 all the way across for each. So 1, 2, 3, 4, 5. So in order to get the radius, we have to realize that the radius in each of these is coming from the height, or the y-coordinate of that strip. So that's coming from the left edge plugged into the curve. So the first one, left edge, or excuse me, right edge plugged into the curve. So the right one, the first right one is a 1. So I plug a 1 in and I get a root x. The second one that I plug in is a 2. So I plug a 2 in and I get a root 2. Same with root 3, root 4, and root 5. So we could leave it like that, or we could multiply it all out and see that when we square the square root, the roots are going to go away. So I'll have 1 plus 2 plus 3 plus 4 plus 5, which gives me 15 pi's. If I look at part B now, it's going to work the same way, and it looks like we're doing, to estimate, we want to partition into 4, and this time we want to do the left endpoint, so they actually tell us which ones to use instead of just saying circumscribed or inscribed. So I've got a solid hemisphere of radius 2. So that means I'm going to have a quarter of a circle that's being rotated around, and we go out to 2. And if I'm slicing into 4, then that means I'm going to be slicing at 1/2, 1/4, or no, I guess we've got a 1 in here, so we'll have a 1/2, a 1, and a 1 1/2, or 3/2. And what we want to do now is use left edges, so it looks like we're still getting the big ones. And we're going to rotate each of those around. So when we rotate, we're going to get that wedding cake on the side again, just like before. Now we've got to add up each of those layers. So each layer is a pi times a radius squared times a height, which in this case, that delta x, is a 2 minus a 0 over 4, which is a 1/2. And we do that for each. Layer. So that radius is going to come from the y coordinate for each left edge. So that means we need to find the equation of the curve. Now notice it came from a hemisphere, which was a circle that had been rotated, and that circle had a radius of 2. So the equation that we're working with is an x squared plus a y squared equals a 2 squared. And we need to have outputs from the x's, so that's going to be, we need to isolate the y, because we need to put the x in order to figure out what the y is. So that's a 4 minus an x squared, the positive root. So the first thing I'm going to plug in, first left edge, is a 0. So I plug a 0 into that, I get a square root of 4. The second edge that I plug in is the 1/2. So a 1/2 squared gives me a 4th. And that 16/4 minus 1/4 will give me a 15/4 in that root. Next thing I plug in is a 1, so that's a 4 minus a 1 squared, so that's a root 3. Next one I plug in is a 3/2, so a 3/2 when I square it is a 9/4, so a 16/4 minus a 9/4 gives me a 7/4 in that root. So if I square then, I'll get a 4 pi times a 1/2, that's a 2 pi. I'll get a 15/4 times a 1/2, that's a 15/8 pi. I'll get a 3/2 pi. And a 7/4 times a 1/2, that's a 7/8 pi. Put that all together, and I end up with 25/4. And I'm done.